needed to determine the performance of a pump. So the most important parameters that are needed to determine the performance of the pump are the following, are these 5 parameters. First, the volumetric flow rate. So the volumetric flow rate is among the factors that determine the performance of a pump, as well as suction and discharge pressures, rotating speed of impellers, input shaft torque or power, fluid temperature at pump suction. We don't need basically this 5th parameter to determine the performance of the pump. If the temperature is playing a role, if we are varying the temperature on the system, then yes, we need to include the fluid temperature at pump suction. Other than that, these 4 parameters are alone sufficient to find the performance of a pump. And what is written here is just to tell you that sometimes you can use a venturi, you can use an orifice plate, you can use a pitted tube, you can use a weighting tank, to get the flow rate. With the pressure, you can measure the pressure using a water manometer, mercury manometer. So basically these are different measurement techniques for the flow rate, for the pressure, for the input shaft power, and the impeller rotating speed. But there is one thing to mention, very important here, which is this. So sometimes you test a pump, okay? Sometimes you test a pump and notice that, for example, let's say that you are testing, let's say that you are taking some data of a pump that is running at one constant speed. Let's say that this is the reading number, and then this is the volumetric flow rate, this is the N, discharge pressure, suction pressure, torque, whatever, right? So the thing is that here sometimes when you take reading for the same pump, the condition changes. Sometimes you might find that, okay, the volumetric flow rate at this point is 1, but at point 2 you took another reading and found the flow rate to be 0.8. So it's a fluctuating behavior of a pump. Specific speed vary as well, like for example one time 1700, another time 1710, and similarly with the other parameters here. So when this happens, you need to determine, you cannot determine, you can use the similarity laws. If you have information like this available, you can use the similarity laws, which are these 3 laws, to determine the performance of this pump at a certain rated speed. For example, let's take this example, and I hope it will clarify things and what I have explained in the previous slide. So let's say that we have a pump driven with an electrical motor, and this pump is being tested in the laboratory. The test result and motor calibration curves are given below. So this is the test result of the pump, okay? So one time the flow rate is 40, the delta B, which is the B discharge minus B suction, is this much, and the unit is PSI. The electric power here is how much? 5 kilowatt, and then the rated speed. Now you see here, for example, the volumetric flow rate is increasing. Remember, here we are assuming that you have to understand this because it's very important. Now the pump in the ideal case, the pump speed should not change, because we are getting the performance curve, we are varying the volumetric flow rate, okay, in order to get the performance curve, and we should not get different numbers of the rotating speed. But because this pump is varying a little bit, okay, the rotating speed is being different for each flow rate. Okay, it is different because the electrical power here, it looks like seemingly here the electrical power fluctuates, which in turn affects the rotation speed of the impeller. So as you can see here, for example, at 5 kilowatt of electrical power, we have a rotating speed of 1775. But if you increase it a little bit, it looks like as you increase the electrical power, then the rotating speed of the impeller decreases. So you have to be, you have to understand this is the performance curve. Okay, this is the performance curve of what? Of this particular pump at this particular speed. But sometimes if this happens, then you need to get the performance curve. You need to get this performance curve, okay, at some rated speed, because the rated speed here was fluctuating. So in order to get the performance curve at one rated speed, and here in this example it's saying that convert these raw data into the performance curves at the rated speed of 1750 RPM. So it wants you to get the performance curve at the rated at one speed of 1750 RPM. So all you have to do is to use the similarity laws to basically find that the performance curve at this corresponding speed. Okay. So these are the motor calibration curves. At this flow rate, the shaft power is this much. So they converted first. You need to convert the electrical power into shaft power. Okay, to convert the input electrical power into shaft power for a corresponding, of course, rotating speed. The main purpose of this step is to be able to calculate the shaft power at the rated speed later, which is here. Okay, so we used the similarity laws, and then we calculated the volumetric flow rate that corresponds to how much? That corresponds to the rated speed of the rated speed. Like we have said that we want to get the performance curves at a rated speed of 750. So this table corresponds to a rated speed of 175. I mean, sorry, 1750 RPM, and that's it. Okay, so then you need to find the flow rate at the rated speed. Okay, and of course the pressure difference, things like that. So the main point is to use the similarity laws in finding the performance parameters, which are the volumetric flow rate, the pressure difference, as well as the overall efficiency and the shaft power at a speed of 750. Okay, right now we'll shift gears into what is called series and parallel pump connection. Sometimes, depending on what is required, you need to arrange the two pumps in either parallel or series configurations. So I know that in many situations you need more than one pump. So you need more than one pump in order to either increase the flow rate of the fluid or increase the head of the fluid. So if you want to increase the if you want to increase the flow rate of the fluid, then you have to put the pumps in a what series. And here we are talking in general here. So whether you have two similar pumps or two not similar pumps. So if the pumps are similar or not similar, if you want to increase the flow rate, then you have to put the the two pumps in parallel. This way you will double the flow rate. So if this pump has a flow rate of A and this pump has flow rate of B, then the total flow rate would be Q sub A plus Q sub B. But sometimes you actually don't want an increased flow rate, but you want an increased head. So if you want to increase the head of the flow, then you put the two pumps in series. And again, whether you are having similar or not similar pumps, but every time you want to increase the head, then you have to put the two pumps in series. And this is the corresponding curve, performance curve. So you see pump A, pump B. Pump A is this much. It looks like these two pumps are not similar. You see, if they are similar and running at the same rotating speed, then this curve should match the other one, okay? But it looks like they are either running at different speed or they are of different sizes. So that's why the performance curve of pump A is different than pump B. But anyway, this represents two pumps being put in parallel, and this figure represents two pumps being put in series. Okay, and yeah, so I'm giving you here an example. This is the single pump performance. Sometimes you have two very similar pumps, and I can tell you that I want you to put these two pumps in series. What would be the corresponding head flow rate? So the corresponding head versus flow rate would be, so if the pumps, like for example, if this is pump A and this is pump B on the same, so if you put them in series, then you will get double head. So the head will be doubled, okay? You see here you have a head, right? So this head will be doubled. But if you put this, and this is H versus Q for series, okay. In the other case, if you put the two pumps in parallel, then what? This is pump. This is the pump performance case of 1, and this is the pump performance curve of 2. But then what? The head will not change. So basically what you will get is an increased flow rate. So the flow rate will increase. Okay, then this flow rate will increase. And of course, depending on where for example, if you put it this way, and then if you put, this is one pump, but if you add another pump, it will add to the flow rate, but the head will be what? Constant. So this is the parallel. This is parallel pump. Okay, and yeah, this is just the example. If the two pumps connect in series, then the head will be doubled, as you can see here. 3200 is double than 1600. Similarly, the 3000 is double the 1500, so on and so forth. But if you put the two pumps in parallel, then the one will be doubled is the flow rate, but the head will remain the same. Okay. There is an important thing here to mention about pumping systems. I wanted to tell you that sometimes, of course, you test the pump, and this is called the pump performance curve. You test how the flow rate of a pump varies, you test how the output, like the hydraulic pump, how hydraulic power varies with the flow rate. But sometimes there is also something called a system curve, and this system curve is dependent on on where the pump is installed in the application. For example, I will give you here an example, a real example. Okay, so for example, here we have two tanks that are put parallel to each other. So definitely there is no elevation head. Since there is no elevation head, the system curve of 1, system curve of 2 is different. Not different, should be. Okay, this is the bump curve, assuming this is the bump curve. System curve 1 Okay, what does it say? The intersection point A of the pump and system curve. Intersection point A of the pump and system curve will determine the pump operating condition of the head and flow rate, the shaft power and efficiency, etc. When the throttle valve installed at the pump discharge is closed. So let's say that we have a throttle valve, okay, here, and one time the throttle valve is open. When the throttle valve is open, like for example partially open, or it doesn't matter, but if it's open, then the system curve will be this, okay. When you close, because remember, when you close the throttle valve, then the system curve will go up toward the low flow rate, right? So it will be shifted from A, the intersection point will be shifted from A to B. So as you can see here, even closing a throttling valve will affect, because at the end of the day, this is just this represents the operating point of the pump, the intersection point of the pump system curve for the performance curve gives you an idea of where the pump is operating right now. But if you close the valve, this system curve will be shifted from this point will be shifted from A to B, and if you keep closing, it will become, at one point the system curve will become like this. No flow rate, high heads. You see, so the system curve is controlled by the characteristics of the flow itself, and it determined by the also where the pump is installed. Because here another example. Let's say that we have two tanks, one tank and the other. The difference between the levels of these two tanks is Z. Since this difference is Z, then the system curve, there is an initial elevation of the system curve of Z. Because also because of the here you have a system operating curve, which is represent the energy level from the lower tank to the higher tank. Imagine that I have reversed it. So basically I have reversed it, that the suction tank is above the center line of the pump, then this Z will be in the negative, okay. And sometimes, like let's read here, if the free surface levels in the tank of both ends are different, such as those shown in this figure in 428b and c, a constant flow resistance will be added to the variable flow resistance. Hence the system curves are shifted upward or downward. Okay, and then this example shows you explains the open system, the system curve very well. So from 1 to 2, the system head, like the variation of the system curve with respect to the flow rate, represent the total, the major and minor losses. So the system curve always represent the major and minor losses. Okay. In case we have two tanks that are at the same level, okay. The system curve, how to calculate the system curve? Because remember, there is something called system curve and performance curve. So the system curve is always the summation of what the major and minor losses. Major losses comes from the friction between the fluid and the pipe material, and minor loss comes from fittings of the pipe. But sometimes we have an elevation head. If you have an elevation head, then you have to add it to the total loss. If the elevation here, for example, if the discharge tank is above the center line of the pump, then you will add the elevation head. You will add the elevation head to the system curve equation. In some cases where you have the discharge tank, like this case for example, you have the discharge tank below the center line of the pump, then you subtract the major losses from the static head, which is Z1 minus Z2. With that being said, I thank you so much